Hi everyone. Um, Today we're finally done with some of the preliminaries of complex numbers, and we can start getting into the calculus. And so, just like in a usual calculus class with complex analysis, we're going to start by talking about limits. Some of it's familiar, but already you're going to see some of the differences that come from dealing with complex numbers. So, first, let me just say what I mean by a function. So these are going to be complex functions. They're going to be functions from the complex numbers to the complex numbers. Although, they may not be defined on the whole domain of complex numbers. So let's choose a set, which is going to be the domain of the function. Call it G. And it's just some subset of C. Then a complex function is a map f from G to C. So let me explain what I mean by this. What do I mean by map? Well, by map, I really just mean a function. So this is a little bit of a weird definition, but in general, what is f? It's just a rule that assigns to every element in G a complex number, which we'll call f of G. So every every x inside of G gets sent under this map to some f of x, which is just some complex number inside of C. Okay. G is called the domain. Of f. And we also sometimes want to consider where does f go? What are all the points that it lands on? So the set of points f of z for all z inside of G, this is called the image of f. And it's sometimes denoted by f of capital G. Okay, so that's what we mean by a function. It's just a rule that assigns to every element of the domain a complex number C. And the domain is a subset of C as well. So it's a map from part of the complex numbers to the complex numbers. Okay, fine. Okay, let's talk about limits. So let's suppose we have a complex function. And I want to talk about the limit of this function for some point. What kinds of points are allowed? Actually, accumulation points. So let's suppose that z naught is an accumulation point. Now, this was so accumulation point was a definition from the last section, section 1.4. And in case you haven't absorbed that yet, let me remind you what it means. So G is some subset of the complex numbers. Z naught's an accumulation point if there's points in G which are arbitrarily close to Z naught. And so maybe I'll write that as just an aside here. So being an accumulation point means there are points in G as close as you want to this Z naught. Okay, and this is necessary for the limit to even make sense. We need to talk about like as we approach Z naught, right? And if the function f isn't even defined for points near Z naught, then we're not going to be able to make sense of the limit, and that's why we need z naught to be an accumulation point. Okay. But if we can talk about points in G approaching z naught, then we can talk about the limit of f as z approaches z naught. So then we say that a point w naught inside of C is the limit of f as z approaches z naught if, now this is going to look familiar, the usual epsilon delta definition of a limit. So for all epsilon greater than 0, there is a delta greater than 0. So these are both real numbers. They're just talking about size, such that for all points in the domain, so for all z in z naught, which are close to z naught, so such that the distance from z to z naught is less than delta. And we don't care about the point z equals to z naught. So one way to say that is we're looking at z whose distance from z naught is greater than 0, so it's not z naught itself, but less than delta. So points other than z naught that are close to z naught, if for all those points we have that f of z is close to w naught. Okay, so let me just rephrase this. So this is saying that the limit of the function f as z approaches z naught is equal to w naught if basically we can get this f of z as close as we want to w naught. So for any epsilon, we can force f of z to be within epsilon distance of w naught by choosing z's which are close enough to z naught. And so we get to choose a delta such that for all z within delta of z naught, this holds. Okay. I guess, I don't know, maybe it's worth saying, so geometrically, maybe this is my set G, contains some point z naught. What are all these points here? What am I really saying when I say that z minus z naught is less than delta and greater than epsilon? Well, I'm choosing some delta, and I'm just saying for all z inside this disk, but not including z naught itself. So inside this circle of radius delta, but not including the center point. So these are the z's that I'm looking at. And so basically what this is saying is that, that f of z for all these blue points is within epsilon of w naught. Okay, so that's pretty standard definition of the limit. The only thing that's really different is now we're looking at z's here in a disk rather than in an interval. And similarly, this inequality defines an open disk rather than an open interval. Okay. Another way to say this, this limit definition is more or less equivalent to saying that whenever z is not quite rigorous, but a good way to think about it, whenever z approaches z naught along a path in G. So we really only care about points in G, right? But whenever I'm approaching z naught along some path which is staying inside of G, then f of z approaches W naught. And by approaches, I just mean gets arbitrarily close, right? The other thing to emphasize in this definition is I don't care. In other words, the definition doesn't depend on what happens at Z naught. It only depends on as we approach Z naught. In particular, the function f may not even be defined at Z naught, right? Its domain is G. All Z naught has to be is an accumulation point of G, but accumulation points of G don't have to be inside G themselves. So they don't have to be in the domain of f. There just has to be paths in the domain which approach Z naught. And so one subtlety here, a subtlety with this definition, which is new, you don't really see it in real analysis or in regular calculus. In C, in the complex numbers, there are many, many different paths which go to a point Z naught. Okay, so let me just draw a picture here. Let's say here's my Z naught. You know, in the real numbers, there's two paths, basically. You can approach from the right or from the left of a number. But now there's many paths. There's this one, this one, this one. And also, and this is actually kind of important, I don't have to choose a straight path. I can come in at a curve. I could choose a path that kind of spirals in towards Z naught and gets closer and closer. So there's all these different ways of approaching Z naught. And what that means is it makes the definition of a limit quite more subtle, because basically what this is saying is you have to approach W naught. F of Z has to approach W naught no matter which path is taken. And so that's a much stronger condition than in real analysis, and it already leads to some new things. So one thing that's new is in real analysis, if a function is kind of simple, if you can write it simply, that probably means it's continuous. Probably means the limits are pretty easy to figure out. And that's no longer true in complex analysis. I can write really simple expressions that don't have limits. So let me give you one example of that. Let's do an example of a case when a limit does not exist. So it's one of the simplest functions you could think of. I'm going to let f of z be equal to the conjugate of z divided by z. So z bar over z. And when is this defined? This has domain. Well, where is it not defined? It's not defined if I have to divide by 0, right? So so its domain is all z in the complex numbers except for 0. Okay. So let's see if there's a limit, if there's a well-defined limit as z goes to 0. Does this limit exist? And so what I was saying before, one way to show that it doesn't exist is to show that if I approach 0 along different paths, let me draw a picture here. So here's 0. If I approach along different paths, what I'm going to show is that I get different things as the limit. And what that means is that this function actually doesn't have, as a complex function, the limit's not defined. So for instance, let's see. let's consider the blue path. Okay, so let's assume that z is approaching 0 and z is real. Okay, so what does that mean? Well, so z is a complex number equals x plus iy, but if we're assuming it's real, then I is 0, right? So z is just equal to x. Then what does this function look like? So then f of z, which is z bar over z, well, okay, so if z is x plus 0i, then z bar is also equal to just x, right? And so f of z, which is z bar over z, this is just x over x. And this is just equal to 1, at least when z is non-zero. And remember the definition of limit here. We don't care about the point z0 itself, in this case, the point 0 itself. We only care about points nearby, and so I'm allowed to simplify x over x to 1 because I'm specifically considering points which are non-zero. Okay, so if I approach along the blue path, then I get 1 as the limit. What about the red path? So let's consider a path z goes to 0. We assume that z is imaginary. Okay, so in that case, z is equal to x plus iy, but x is 0 here now, right? It's purely imaginary. So z is 0 plus iy, which is iy. And z bar then, the conjugate, replaces the imaginary part with its negative. So this is equal to negative iy. So then what do we get? Well, f of z is going to be equal to z bar, negative iy, over z, iy. And again, we're assuming z is non-zero, so y is non-zero in this case. And so this simplifies to minus 1. Okay? And what this is saying is that the function f has a different potential limit depending on which path I choose. And what that means is that the limit doesn't exist. Okay, because there's some paths where I'm going to get 1, there's some paths where I get minus 1, and so there's no well-defined limit. Does not exist. And so as you read the textbook on your own for this section is section 2.1, by the way, you're going to read proposition 2.2, and the book phrases it in kind of a technical way, but it's about exactly this idea. So when you read proposition 2.2, you should think about it this way. If you can find different paths in G, where f has different limits, along those two different paths. So I should say paths like approaching some z0. And f has different limits along those paths, then the limit of this complex function, f of z, as z goes to z0, does not exist. Okay. So that's what that proposition's about, just in case you read it and get confused. By the way, a fun exercise for you would be to figure out what what this function looks like, what its value is approaching as you go along the purple path. So I'll leave that as an exercise. It's kind of interesting to try different paths, not just the real and imaginary ones. Okay, so once we've talked about limits, then we can define what it means for a function to be continuous. So a function f with domain G okay, so sorry, let me set this up. So let's say we're given a function f and we're given a point z0 inside of G. And now I'm assuming that the point's actually in G. I need that to talk about f being continuous there. Then f is continuous at z0 if exactly what you would expect, the limit of f of z as z approaches z0 is equal to the value of the function at z0, equal to f of z0. So if z0's not an accumulation point, then the limit doesn't make sense. That's sort of a silly case. It's not that important. So or z0 is an isolated point of G. That's not so important. But the point is that continuity means that whenever you have a path in G that goes towards z0, then f of z along that path approaches f of z0. Okay. There's a little bit more in the book, basically a bunch of the usual theorems about limits and about continuity. For instance, the limit of the sum of two functions is going to be the sum of the limits, things like that. But I'll leave those to you to read on your own, and let me know if you have any questions.